The first lab was pretty straightforward. I thank you for those who typed it. Just trying to read a lot of people's writing was a big problem on some of these. So this is why I put these labs on Blackboard in Word, so you can download them and just type them in. But let's see, some comments. When you're doing physics labs, first thing you want to do, and this goes for the next lab as well, in the next all the labs, there's a rubric on Blackboard that is, I posted it there for a reason, that shows how I grade and what's expected. So have that with you when you're writing up your lab, just so you know, it's like what's the professor want? That's what people always ask. It explains exactly what I want on there, so just follow that. Okay? It's a good guideline for this lab and any lab. But one of the things about physics is clarity. It's true of engineering and science in general. When you're writing a lab, the purpose of the lab is to either validate known theories, which is kind of what we do here, or to document scientific phenomenon. And clarity is really important. So how you present the material, how you write it, is extremely important. I make my students try to be as objective as possible in their labs. And I think I've surprised this before, like when you're writing, how did your results compare to the theoretical? I'm not looking for, they were really good, because that doesn't tell me anything, or they were pretty close. Pretty close is nice, but space shuttles can fly out, fall out of the sky if things are pretty close. So you want to be exact. So when we do labs, like we're going to be doing Snell's law experiments next week. Basically, we're calculating the index of refraction. And we know what the known values are, and what you're trying to do is validate that. So if you come to, and we always calculate percent error, so if you come in within 3% of the theoretical value, it's not good enough to write, my answer was close, okay, or what we came up with was close. All you have to write is, my answer came to within 3% of the theoretical value. So it's very exact, So just try to be as clear as possible in your writing. That's I always. So that said, and try to be neat, because I can't read half your writing. Let's see, Jacques, Ali, Christina, Josh. I try to comment on your labs a lot as well, just be correct for Benino.
Yes.
Okay. Try to be helpful. Christoph. Dave. Brian. And Alex. Okay. So today we're going to continue, actually we're going to finish chapter 1, laser safety. Just to recap what we've done so far, we talked about the different classifications of lasers. And this, I don't expect you to remember the classifications of lasers from exam or anything, but just so long as you know that they exist, and you can always look them up. But some of the important ones are class 1. If somebody wants you to work on a high-powered laser, just make sure it's class 1, unless you're in the laboratory and a research scientist. Class 2, class 3A, class 3B, and class 4. Class 4 can burn stuff, but if you contain class 4 laser in an enclosure that keeps it safe, it becomes a class 1 laser. Class 2 and class 3A are the most common types of lasers that we use in this program anyway, because they're relatively eye safe. You're not going to kill yourself with one of these things. However, class 3B, we do have those lasers too, and it's important to adhere to safety precautions. We talked about the engineering controls, the administrative and procedural controls, and protective equipment to help keep you from killing yourself with lasers. It's always good to know these things. Then we talked about the maximum permissible exposure. This is the important thing. If you take it, your takeaway for Chapter 1 is know how to calculate the irradiance of a laser beam and then be able to compare that to the maximum permissible exposure so that you can determine whether the laser is safe or not, high safe. And also we're going to be using today the irradiance to calculate the optical density of safety goggles. How do you know if a pair of safety goggles is appropriate for the laser that you're using? How do you spec them out? All right. We talked about the maximum permissible exposure. Remember this? Okay. If you forgot all this stuff, by the way, I have the videos from this class are up on Blackboard now, so you can go back and review them when we talked about it. We talked about the different parts of the eye. Okay, what parts of the eye are affected by ultraviolet, visible, and infrared light. We showed some burn patterns and corneal burns, retinal burns, and then we calculated the irradiance. And I do have a take-home quiz today, basically one of these problems, just like this. You calculate the irradiance. Irradiance, again, is basically the power density, how much power is concentrated in a certain area of a laser beam. If it exceeds 2.5 milliwatts per square centimeter for visible light, then you have a problem, because that's the maximum permissible exposure for visible light. So know how to calculate the irradiance. We'll do a couple of examples, and this is where we pick up today. Today we're going to talk a little bit about something called the nominal hazard zone. And let me just kill the light and give this glare on the screen. Thank you, sir. All right. Nope, not both of them. Just, leave one of them on. Yeah, it's good. Okay, so nominal hazard zone. Yep, that's good. Nominal hazard zone basically defines how far away from a laser that is being focused with a lens, how far away you have to be before that laser becomes eye safe. If you look at the picture here, we have a laser beam that has a beam coming out, and most lasers, depending on what the application is, are usually focused if you're doing materials processing, or expanded and collimated for whatever application. So if you have a high-powered laser and you're focusing this, obviously right at the focal point, it's like a magnifying glass in the sun, you're going to burn stuff. It's going to get hot. But as you move away from that and the beam diverges, how far away do you need to be from that laser before the beam diverges sufficiently such that the maximum permissible exposure is less than 2.5 milliwatts per square centimeter, for visible assuming. So, and that's known as the nominal hazard zone. There's an equation for a nominal hazard zone, which says that if you take the focal length of the lens, okay, what focal length lens you have, and you divide it by the diameter of the beam as it enters the lens, and then multiply that times 4 times the power of the laser, divided by pi times the maximum permissible exposure for that particular laser. This thing here, I know raise something to the 1/2 power. What does that mean? It means that I didn't have the math equation editor available when I put these slides together. Something raised to the 1/2 power just means the square root. So calculate this stuff and just take the square root of that. Okay, so I'll have to edit that in my notes. But it's a pretty simple equation that you can plug into, and it will tell you how far away you have to be. For example, if you have, let's say, determine the nominal hazard zone for a 1,000-watt CO2 laser, okay, typical industrial laser. From the focal point of a 20-centimeter focal length lens, assume that the beam diameter is 3 centimeters. And these are reasonable numbers. These are typical numbers. From the maximum permissible exposure table for that laser, carbon dioxide, if you look it up, that's an infrared laser. Okay? And the maximum permissible exposure that's listed for that is 0.1 watts per square centimeter. Okay? So we know what the MPE is, just as you look it up on a table. If we plug that number in to this equation, okay, 20 centimeters, I should have put the centimeters in here, divided by 3 centimeters times 4 times 1,000 divided by pi times 0.1. You come up with 7.52 meters for this laser. Think about that. What's 7.52 meters?
Inches.
It's
How many feet is that? Just for the ballpark.
21 and
Yeah, so it's like a little over 20 feet away, right? So if you think about that, I have a laser. It's coming out. Okay, it's going to a lens. Let's say the lens is like that big. Okay, it's focused down, and then it starts spreading out. It starts diverging. For that particular laser, 1,000 watts, it's a lot of power. You got to be about 20 feet away before the irradiance of that goes down to something that's less than 0.1 watt per centimeter squared. That's all it's saying. We kind of did this problem, except the beam wasn't being focused with a lens, but when we did the lab on laser safety, this is basically kind of what we were doing. How far away do you have to be? What happens to the beam as it travels a certain distance and spreads out? Basically, the irradiance goes down because the beam is getting bigger. So this is a typical calculation that if you're working with industrial laser, you should be concerned with. Yes?
Does the color of the beam actually play a part, like the MPE is based on the color of the
Yes. Yeah. The maximum permissible exposure is based on the wavelength, the color, correct? Yeah. So you just have to look up, the type of laser, it'll tell you the wavelength, and then just go across the table and find the value. I have an example for you. Why don't you guys do this one? Determine the nominal hazard zone for an 8-watt argon laser, which is the laser we have down the hall, from the focal point of a 15 centimeter focal length lens. Assume the beam diameter is 5 millimeters.
equation?
I don't know. Oh, it's argon. Sorry, argon laser is a visible laser. It's a green laser. So the MPE, if you look it up, for all visible lasers are 2.5 milliwatts per square centimeter. So I should try to crank that one out. Give you a couple minutes. See what we come up with. I'll put the equation back up. Actually, you know what? I'll just write the equation. This, like anything else, depends on getting the units right. If you set up the equation in a way that you can check your units, that's why it's always important to include units. So we've got nominal hazard zone is equal to focal length divided by the diameter of the beam times the square root of 4 times the power divided by pi times the maximum permissible exposure. And just remember, maximum permissible exposure is 2.5 milliwatts per centimeter squared.
So that would be the 8-watt,
Yep. So
8 times.
this is 8 watts. Okay. Now, if you're using, this is why the units are important. If you're using watts for this one here, if you go to the MPE table, this is, you have to use 2.5 times 10 to the minus third watts, because that's what milliwatts means, watts per centimeter squared, so that the watts and the watts cancel out. Okay.
Where did you find the MP level?
Where?
The table, what did you find?
Or you can go point
So
0.
where did I find the table? This?
Yeah.
Where?
This comes from the table in your notes. Right there. So for argon laser, here's the wavelength, maximum permissible exposure for a quarter second blink response, 2.5 times 10 to the minus third watts per centimeter squared. Okay. keep in mind that the focal length was given in centimeters, the diameter is given in millimeters. Is that? Oh, no. Yeah, the diameter is in millimeters. Right. So make sure that those units are the same.
Can you repeat that?
Say again?
The
I said-
focal is measured in,
The focal length, F0, is 15 centimeters, okay? And the diameter of the beam is 5 millimeters. So when you divide these two numbers, either convert this to millimeters or this to centimeters. Because you have to make sure those units are correct. Race to the answer. Anybody have anything yet?
The wrong answer.
How do you know that?
It's too big.
How do you know? Let's
Because the other one was so much more powerful.
Good question. The
Yeah,
other one
I
was
think,
more- That's a really good point. Sometimes it's not intuitive. The laser, the carbon dioxide laser is infrared, okay? It actually has a much higher maximum permissible exposure because it's not, the infrared doesn't go through to your retina. It actually gets absorbed at the surface. So your eye can withstand a lot more.
2500?
I got 19.149 centimeters squared.
No,
Or
meters.
meters.
Meters?
Meters,
Yeah.
not squared.
Not squared. Well,
Yeah, just-
nominal hazard zone is a distance.
Just meters.
Meters, okay. Anybody else?
That's what I got.
That's what you
Sounds
got?
too big for me.
No, well, let's calculate it out.
Well, I guess that is where.
Because you convert the 5 into 50 centimeters.
I got 25 meters.
You got 25 meters?
25.5.
25.5?
Yeah.
All right, so let's figure this thing out. So focal length, 15 centimeters. We got 15 centimeters divided by the diameter, which is 5 millimeters. 5 millimeters is how many centimeters? 0.5, right? Okay, there's 10 millimeters in every centimeter, so this is 1/10. Okay, that times the square root of 4 times, how much, what power do we have? 8 watts? Divided by pi, times maximum permissible exposure is 2.5 times 10 to the minus third watts per centimeter squared. Let's look at the units here. Centimeters cancel centimeters. Watts cancels watts. Okay? When we have 1 over centimeter squared, just gives us centimeters squared. But when we take the square root of something that's squared, we end up in what? Centimeters. Right? So the answer, the way we have this written out, is going to be in centimeters because of how things canceled out. And if we crank these numbers out, we'll just check this out here. Okay, so I always do everything under the radical first, and then multiply it times whatever's on the outside, order of operations. So I have 4 times 8, which is 32, divided by pi, was that, divided by 2.5, which is 10 to the minus third, was that, and I take the square root, was that, times 15, was that, divided by 0.5, equals that. Okay, so I get, in centimeters, this is how you know what your answer is. I get 1914.92 centimeters, okay? So if we take and move this decimal point to the left by 2, okay, because there's 100 centimeters in a meter, okay, we end up with 19.1492 meters. Good. So,
The only thing I did was, instead of the 5, I put it as a 50, so it would just bring me straight to meters. The .5?
Oh, this here?
No, the .5 divided by 15.
Oh, over here, okay.
Yeah, I just changed it to 50,
Okay.
bringing me straight to meters.
You changed this to 50?
Yeah, and it brought me to the 14.149 meters. I accidentally put the 50, and it got me that answer.
Okay, well, I'm not sure how that worked, but.
Yeah.
But that's how you do it.
Okay.
So, one of the things.
He was dividing by 0.5 centimeters times 100.
Just combine the times.
You just combine the last two steps.
Oh, I see, okay, I see, because this ends up in centimeters.
Yeah.
Okay, you converted that to centimeters across, okay, got it. Yep, okay, yeah, do it that way.
Okay.
Okay. So, I noticed on the quiz that some people still had some problems converting centimeters to the millimeters, I forget what the actual numbers were. But again, if you go back to the equality thing, you know, if you wanted to convert centimeters, let's say, you know, 425 centimeters to meters, okay? The safe way to do it is, if you know how many centimeters there are in a meter, you just multiply it times 1 meter, divided by 100 centimeters, because there's 100 centimeters in a meter, so these are exactly the same, right? So it means just multiplying whatever it is times 1, but that cancels this, that cancels that, and 425 divided by 100 gives you 4.25 meters. So if you're not sure, use the equality. It's just an easy way to do it. I mean, I still do that. If I have to convert centimeters to inches, I go back to 7th grade when they told me that 2.5 centimeters equals 1 inch. I was like, oh, okay. If you know that relationship, then you can convert meters, centimeters to inches, to feet, to miles. You know, you just keep multiplying it times equalities until you get the unit that you want.
I'm still coming up with 15.15.
Okay.
Is that-
15.15. What kind of calculator do you have? This is. Oh, this is the one that you have to plug it in. The answer, right? This is, hold on.
Yeah, okay.
Let's see. So, so when you do this, do you have to do square root first?
Yeah, second, yeah.
Okay, so you do second.
Square root. It's on the left.
There it is. Okay, so under this thing,
Yeah.
you have
32.
4 times 8, that goes parentheses, divided by. I bet you I know what you did. Times 5.
Then you have to hit second, and then hit 2.
There it is. 3 times 3, close parentheses. Okay. So, the problem with this is when you're, if you hit square root first on this kind of calc, that's why I don't like these calculators. If you hit square root first, it automatically gives you a bracket. So you start filling this in, you close that bracket, okay? And then you want to divide it by this, so you get another bracket. I think what's happening is it's taking the square root of 32 and then dividing that answer by this. I think that's what's going on here. Because it's hard to see that everything gets under the square root sign. So that's
What calculator?
so the that's why.
I thought it was TI 30.
It is. This is a TI-30XI. I'm sorry, XA.
XA.
Yeah, you have the XS, or the 2S.
Too many.
Too many.
TI 30 XA.
That's the same as he's got.
Those are the right answer.
In HP11, so
Okay,
you can
so-
do everything in
How did you
RPM.
do it?
It's great.
You might want to show him how to do that later.
It's just, that's a.
You did parentheses
Yeah.
around everything?
Yeah.
Just have to remember that you have to do it.
Yeah, try.
Yeah.
And that's the thing, once you
Divide.
figure it out, then you know how you're
Yeah,
calculating.
those are,
It's the typical
those are
same,
fun.
same answer, but it's like instead of time to the negative 3, it's the 3, positive 3.
Your answer's the positive 3?
Yeah.
Or he can put 2,
But I got like 1,
You like 1.9,
1.4.
put 2 and 4.8,
Okay,
close it, multiply,
so you can do everything under that radical first, then take the square root of that answer. Maybe that's the way to do it.
because I did like that. And it's half with 2 first,
Okay,
and end with 2. So it can be more 10 answer.
same answer?
Yeah.
Okay. All right, well, like I said, I've been using this since 1976. It's gotten me through. Right next. All right, so let's move on here.
All good.
Okay. So now we can calculate this, right? We're good?
Yeah.
Nominal hazard zone, as long as you understand the concept that you want to spread the beam out enough to reduce the irradiance to something that's less than the maximum permissible exposure. All right. Now, before I actually move on, I have a lot of people who, will ask me, it's like, why do we have all these equations? Why do we need equations, Dave? Why are equations our friends? They're not just there to like mess you up.
Somebody else has done the legwork for us. So that-
Somebody's done the legwork and came up with the equation, but these are tools. These are tools for modeling physical phenomena. Okay? So if I look at this equation and I say, geez, I wish the nominal hazard zone was less than 10 meters. Okay? You look at the equation and say, well, what can I do? Based on the equation, what can I do to reduce that nominal hazard zone? Yeah. If you want to make this smaller, okay, one thing you can do is make D bigger, right? If you make the diameter of the beam bigger, just by looking at the equation, anything divided by a bigger number creates a smaller number. Or I can make the focal length smaller. If I have a shorter focal length lens, what does that mean? That means that the light's going to come to focus a lot faster, but it's also going to diverge a lot faster. So it's going to spread out faster. Okay? I could lower the power, okay, but who wants to do that? I always have to have more power, right?
Yeah.
Maximum permissible exposure is what it is. So there's really not a lot you can do over here. But you can manipulate the beam parameters to give you the answer that you want. And that's what equations are used for. They're used for modeling physical phenomena. I'll leave it at that. They're your friend. So we're going to shift gears a little bit here. We're going to talk about the attenuation of light. So you've got lasers, you've got light sources that are really bright, and you want to protect yourself. Okay? The idea is to put on a set of glasses that will absorb a certain amount of light. Okay? Well, there's something called the exponential law of absorption. Okay? I don't expect you to know that, just how to use it. Okay? The exponential law of absorption says that the thicker you make a material, light is going to be attenuated or knocked down in power at a rate that's exponentially proportional to the thickness of the material. So the thicker the material T, the more it's going to get shrunken down as it goes through. And you can model that using that equation. T means transmission, how much light is going through. And if you look at those parameters, you have the natural log E raised to the minus kx. I'm not going to ask you to do this on a test or a quiz, so I just want to know, I want you to know where this comes from. But if you look at the equation, E is just a natural log, it's just a number. So you raise a number to a negative exponent, okay? Anything raised to the negative power, the bigger that power becomes, the smaller the number gets. So when there's an exponential increase or decay, it decreases at a decreasing rate. Okay, that's what it is. So if you look at that, the T is a transmission, K is something called the absorption coefficient of the material. The larger the absorption coefficient of a material, the more that material absorbs. So depending on what material you have, and you look at any one of the materials handbooks, it can tell you what the absorption coefficient is. Higher absorbing materials, obviously, are going to make the transmission less because that exponent gets bigger. Or you can increase the thickness, okay? X, and this is the thickness of the material. So if you wanted to mess around with the math, okay, let's say you wanted to solve for that absorption coefficient. What is it? Okay, well, if we have the transmission equation, we're going to do a little logarithm trick here. If you take the natural log, which is similar to the log base 10, but ln is the natural log 2.7 something, or 2.3, I think. I forget what it is. Natural log of both sides. Okay, we take the natural log of one side, take the natural log of the other side. This power, okay, it's basically taking the inverse of this, so this whole side just becomes whatever the power is. So you can extract the exponent from that e function there. So negative kx is equal to natural log of t, and you can just solve this algebraically by dividing both sides by negative x. So k becomes negative ln t divided by x. One of the properties of a logarithm is if you take 1 over that number inside here, this becomes positive, or vice versa. So we can rewrite this equation this way if you wanted to solve for it. So if you know how thick your material, again, it's the modeling equation. So if you know how thick the material is you want, I want the safety glass to be 2 millimeters thick, okay? I want the transmission to be 50%, okay? Plug it into the equation, it'll tell you what material you need based on the coefficient of absorption. So you just find the material that kind of matches that. And then that leads to this, okay? When we look at safety goggles, and I'll grab some, I showed to you last time, but I'll bring it back up in a second. When you need to calculate safety goggle, what safety goggles do I need for a particular application? There's a number called OD. OD is the optical density, that's what that stands for, OD. OD, 0, 1, 2, all the way up to whatever, means if I take that number and I plug it into, if I raise 10 to that power, okay, that tells you how much it's going to knock the light down by. So if I have a goggle with an OD3, okay, what that means is that those goggles will knock the power down by a factor of 10 to the third, or 10 to the fourth, or 10 to the fifth, or 10 to the sixth, okay? 1,000 times, 1,000,000 times. So if you look at the OD number for glasses, all it tells you is take that number, raise 10 to that power, and that is how much, the factor by which those goggles will reduce the intensity of the light coming through. So to calculate it, we know what the maximum permissible exposure is for whatever laser we want. You just look at the table, right? So if we know what the maximum permissible exposure is, if we calculate the irradiance, and here I express it as I0, and you guys have calculated irradiance a bunch of times already, right? Okay, watts divided by centimeters squared. If you take one divided by the other, and then just take the log base 10 of that number, that gives you the OD number, okay? And all this does is says, if I have an irradiance that's 1,000 times greater than the maximum permissible exposure, okay? What do I have to raise 10 to in order to give me 1,000? Okay, if this is 1,000 times bigger than this, then you have basically log base 10 of 1,000, right? 10 raised to what power gives me 1,000? 3. Yeah, so you have OD3. And that's all. So if we look at that as a calculation, let's do an example. Let's say we have a neodymium YAG laser. It's got a power of 40 watts. Okay, that's a typical laser that's used for marking and etching metals, ceramics, not ceramics, but metals, like a trophy shop kind of thing. Let's say that is projected onto a fully dilated human eye with a pupil of 7 millimeters, or 0.7 diameter. So all of that light, the diameter ends up being 0.7 centimeters right on your eye. The eye is exposed for a duration of 10 seconds. Wow. Yeah. Why do they do 10 seconds, by the way?
To kill the person.
Well, you could blow his eyeball out, definitely. But
Nice,
for
number.
neodymium YAG is an infrared laser. And the reason that they came up with, it's like, why 10 seconds? Well, for visible, you could see it. So your natural response is to blink and turn away, and they measure that on average about 1/4 of a second. That's why you have the 0.25 second response time. Infrared light, by the time, and they've done this through research, it takes you about 10 seconds to realize you're being fried. Okay, so for a 10-second exposure, okay, going back to that table, the MPE is 0.0051 watts per centimeter squared, okay, or 5.1 milliwatts per centimeter squared. Okay, again, so you have to look at the time also of the exposure. So for this one, we're trying to figure out what goggles do we need to protect against this kind of exposure. So what we need to do is figure out what the irradiance is of that laser on the eye. So we have a 0.7 centimeter diameter on your beam. So we plug it into the area, pi p squared over 4. So pi times 0.7 squared divided by 4 gives us 0.385 centimeters squared. That's the area of that beam on your eye. Okay. To calculate the irradiance, the optical density, we know that we have to calculate the irradiance. So what is the irradiance? And in this equation, I'm just going to confuse you a little bit. I'm going to plug everything into one big equation before I solve it. So to calculate the optical density, we have the log base 10 of the irradiance, which is power divided by area, divided by the maximum permissible exposure. If we plug our numbers in, we have 40 watts divided by 0.385 centimeters squared, which gives us the irradiance, and then divide that by the maximum permissible exposure for this particular laser, making sure that watts on top, watts on the bottom, centimeters on the top, centimeters on the bottom, okay, everything cancels out. But if you do this, you come up with 4.3 for those goggles. Okay, 4.3. If somebody says, here's a set of safety goggles, the optical density is 4.3. What does that mean? By how much is light going to be knocked down by those goggles? Over 10,000 times. So 10 to the 4th is 1,000, so it's a little bit more than 10,000, a little bit more than 10,000. So, so if you were buying these and you go to these, the laser safety goggles store, and they only have OD4 and OD5, which one would you pick?
5.
I'd probably pick 5. 4 is not enough. You're still going to get more irradiance on your eye than you need to. So always err on the side of, be conservative, go a little higher. Yes?
This is a quick question. Welders, they, what range are they?
Good question. I don't know offhand, but they're pretty dark. It's probably an OD6.
Okay.
Yeah.
Should say it.
It should, yeah, it'll say it. As a matter of fact, hold that thought. I'll show you.
Yeah, no, I used to weld out that. I never dawned on me that. Exactly. What do you call welders have a short lifespan on their eyesight?
What about the welding ones that come on, like with a battery, like?
Oh, those,
light, and then
yeah,
they flag,
those are
they have
liquid
those
crystal. Yeah.
for lasers.
I believe they do actually.
Really?
Yeah, I mean, it's a liquid crystal at that point, and you can make the density whatever it is. You can tune it in.
Yeah.
But these goggles, okay, these are blue. Anybody play golf? Ever have those blue ball finder glasses? All this is a blue safety goggle. Yeah, it makes the white pop when you look at it in the grass. But this is spec'd out for ruby laser and for helium neon laser. Ruby is 694.3 nanometers, just on the edge of the red part of the spectrum. Helium neon is 632.8 nanometers in the red part of the spectrum. At the ruby wavelength, this is an OD6, which means it knocks that light down by a factor of 10 to the 6, or a million times. So that's a lot. For the helium neon, which is red, a little shorter wavelength, it's OD5. So this knocks it down by a factor of 10 to the 5th, 100,000 times.
How bright or how powerful is the laser going to be? You can still see it with those on.
Good question. I'm going to show you another pair in a second to answer that question. So, one thing you have to remember that these are very wavelength dependent. Okay, this filters out red. Red will not go through. I don't have my red pointer with me, but it doesn't allow red to go through. But there it is. The green goes through. Okay, it knocks it down a little bit, but see the green going through. This would be a brick wall to red, and nothing would go through. However, these are in the right case. Nope, more blue ones. So, somebody's sticking the wrong goggles. I've got other goggles that come in a case that looks like this, they're designed for green light, okay, for argon light. And you pass the green light through it, nothing goes through, it's a brick wall, but they have like an orange tint to them. So you see orange goggles, those are usually meant for green lasers. And to answer your question, sometimes you want to be able to see your beam. Like if you're using a, like the 8-watt argon laser that we had the previous problem, you're aligning an optical system, okay? And it's hard enough to align an optical system, especially if you can't see the beam. So you want to see some of it. So you want to knock it down just enough to protect you from a stray reflection or something like that. You know, if something gets reflected off a doorknob or a ring, you know, momentary, it'll protect you from that. But it's not going to protect you from a straight shot in the eye. So, for example, if I was operating that green laser down the hall, it's 1 watt. The goggles I have an optical density of 2. Optical density of 2 means it's going to knock that light down by a factor of 100. Okay, so 1,000 milliwatts, or 1 watt, 1,000 milliwatts divided by 100 gives you 10 milliwatts. Okay, and if you look at that as, you know, knocking it down to protect you against 10 milliwatts, you got to make sure that your radiance, depending on how big the beam is, you know, does that. It's going to be greater than the maximum permissible exposure. So, but it's enough to protect you against a stray reflection, or, you know, something gets scattered and hits you in the eye, but not from a direct shot in the eye. Something like this, you know, 4.3 is designed to completely knock this particular wavelength down to a level that's safe. These don't have anything written on them. Oh, there is. Carbon dioxide. Interesting, carbon dioxide, you know, a laser like that made by Trump, 1,500 watts, you know, you can cut inch-thick steel with that. Regular glass lenses will protect you against that. This has an optical density of minimum of 15 at 10.6 microns. So 10 to the 15th power. So this literally is like a cinder block. You know, nothing's going to go through this thing at that wavelength. It's just going to sit there and melt the thing like this does. So depends on the wavelength. That's important. Okay, and depends on the power level of the laser and the irradiance that results from that power level. Those 3 things are what determines what type of safety goggles to get. Before we do that, there are a lot of places where you can get safety goggles: lasersurplusparts.com, prlog.com, .org, madeinchina.com. There's one place that's probably the premier. Actually, there's a couple places. We get all our laser safety stuff from a company called Kentech. It's up in New Hampshire. The owner's name is Ken. But Kentech makes some really good stuff. Goggles, by the way, are not cheap. These goggles that I was showing you, those range anywhere from like $300, $400, $500 a pair. When we go on a tour of Newfern, we'll go into the lab where they're building, testing the lasers. They have, you know, spare sets of goggles around, but they watch them very carefully. You know, it's like, those are mine. You know, don't mess with my goggles. People take them very personally. All right, so let's do this example. Okay, if you can do this, then you can do the take-home quiz. Crank some stuff out here. I do these because I want to make sure that you guys can do these calculations and that there's no questions. If you have questions, please ask. Okay, so we got a helium neon laser. Helium neon laser is a visible laser. It's a red laser. Okay, so let's say it's got 35 milliwatts, 5 millimeter diameter, and it's projected onto a fully dilated pupil, 7 millimeters in diameter. The eye is exposed for a duration of a quarter second, calculate the minimum optical density. So if all the laser is assumed to go right on the pupil, assume the diameter is 7 millimeters. Okay. Calculate the irradiance, and then use the equation for optical density to tell me what safety goggles are needed. I just while you're doing this, I set up another field trip, March 23rd, Wednesday, 10 o'clock in the morning for Arcor Laser. It's in Suffield, Connecticut. It's a laser machining shop. So if you guys are interested, I'll have a sign-up sheet for that coming around next week. They do some cool stuff. A lot of medical device manufacturing with lasers.
What day's that one?
That's Wednesday, March 23rd. It's after the Wednesday after spring break. Anybody have any answers? 4.24. Anybody else? Yes, no? Dave, what'd you get? Not yet?
I'm slow.
I thought you did this in your head. Alex, you got a number yet?
No, I'm still slowly working it.
Christoph, anything?
Working.
Working on it? He's very methodical. Precision.
1.4.
Did you get
0.54.
I have to correct my hair, so
What'd you get?
I'm still
Oh, you're going back? Yeah.
I haven't supposed to.
Did Dave shake your confidence?
Yeah, I think that's it.
We were using 5mm for RD, not the 7.
I'm sorry, say
I
it.
thought we were using the 5mm for D, not the 7.
Oh, I'm sorry, yeah, you're right. I got that, I copied it wrong. You are right. That's why I have you people correct me.
Occasionally pay attention. Yeah, I've done a lot of this calculated before. I assume I just push the log button. Doesn't have.
Yeah, so this problem, you've got an eyeball that has a 7mm pupil, and the laser beam is 5mm, so all of it's going into your eye. All right, let's do this again. 0.5 squared. Is that this comes out to 0.196 centimeters squared. Okay. If we do step 2, we just calculate the irradiance. The irradiance is 35 milliwatts divided by 0.196 centimeters squared. 178.25 milliwatts per centimeter squared. Okay, so that's the irradiance. Now, just looking at that number, okay, you know that the maximum that you can have for your maximum permissible exposure is 2.5 milliwatts per centimeter squared. This is 178 milliwatts per centimeter squared. How much do I need to knock that down by to get me down to the 2.5? That's what that equation is saying. So if we take these numbers, plug it in over here, we get log base 10 of 178.25 milliwatts per centimeter squared divided by 2.5 milliwatts per centimeter squared. Okay, these units cancel out. Take that divided by 2.5. What's that? We have to knock it down by a factor of 71.3 times. Take the log of that. We come up with a log number of 1.85. 1.853, that's what I got. Which, if you think about it, does that make sense? This is a sanity check thing. If you know you got to knock it down by a factor of 78, point whatever, times, okay, 78, what do I have to raise 10 to give me 78? Well, if I raise 10 to the first power, that's 10. 10 to the second power is 100. So it's somewhere between 1 and 2. So this is pretty close. So the 1.8, all right, you're in the right ballpark. That's how you kind of check to make sure you're on the right track. If it makes sense to you, if you come up with like 48.9, it's like, okay, I probably did something wrong. It's like shiny the black table here, But did anybody come up with this?
Yeah.
Okay.
Yeah.
So if you were going to buy goggles to protect you against this laser, and you had your choice between, OD1 and OD2, which one would you buy? 2. Okay. You always want to be a little overprotective to knock it down. If you ordered goggles that were 10 to OD6, you'd never see the beam. You probably wouldn't see anything else either. But at least it would protect you. Okay, so can everybody do this? Okay, that's why I did all the steps. So just to summarize some of the safety rules for all lasers, regardless of the wavelength and the power level. So a lot of this stuff is common sense. Okay, first, avoid looking directly into any laser beam or at its reflections. That goes without saying. Don't ever stare into a laser beam. It's not a good thing. Remove all unnecessary, shiny, specular, reflecting surfaces from the work area, especially if they're higher power lasers. And that includes watches, rings, and anything else that could reflect. Ball head, yeah.
It's very shiny.
That's true. Operate lasers in well-defined areas in which access can be controlled. The area should be posted with appropriate signs to alert persons passing through that area that a potential hazard exists. Again, that's why we have laser signs on every door in here. Even though whether you're using them or not, they're in here, so people need to be warned. The laser system should be operated only by or under direct supervision of a person who's knowledgeable of the hazards and control methods for both beam and non-beam conditions. That means laser beam and electrical also. The individual is usually a laser safety officer or the LSO who is designated by the administration of the company, hospital, or educational institution. The LSO shall have the authority to be and the responsibility to effectively monitor and enforce the control of laser hazards and achieve the knowledgeable control of laser hazards. Did I ever tell you the story about the Mass Department of Radiation Control? 1991. I had just purchased that 8-watt argon laser down the hall, and we had a campus safety officer at that time. We still do, I don't know who it is. But somebody found out that we have lasers up here. It's like, oh my God, you guys have lasers up there. Shut everything down, stop everything until I get my hands around this, So this safety officer said, just calling me, saying what's going on. Calls the Mass Department of Radiation Control. These are the people that certify hospitals for like radiation safety, for x-rays and things like that, and lasers, as a matter. But they called the radiation office, and they're like, well, we don't really deal with laser stuff. This is more hospital, x-ray equipment and stuff. But there's a guy at Springfield Tech that you might want to talk to. His name is Nick. So yeah, it was pretty fun. Anyway, if you ever have a laser accident, lastly here, always report it, just to be safe. If you get hit in the eye with a laser and you're concerned about that. Again, the lasers we use in our lab here, I've been in the eye a million times. As long as you blink and turn, you might get a headache. It's like looking at a laser torch, but it goes away. It's not a problem. However, if you are working with anything that's over a class 3A and you get hit in the eye, you probably want to have that checked out. Go to your eye doctor just so they take a picture of your retina. We used to have students. We used to mandate that students had an eye exam before they came into this program, took any courses, just to avoid any problems that I hit with the eye, in the eye with a laser. Lawsuits. Lawsuits. It wasn't me. It was the administration back then. This was like 20 years ago. They kind of loosened up those requirements because lasers are everywhere now. We've got laser pointers and stuff, so we're like whatever. But it's always good to be on the safe side when you're working with lasers. And that's it. So for today's lab, because we've missed 2 Tuesdays, the Tuesday class is 2 weeks behind the Thursday class. And everybody's done the laser safety, or the Tuesday class has done the Thursday class has done the laser safety lab, which was lab 2. However, if we do the third lab, which is Snell's Law, we haven't gotten into that yet. The third lab is on chapter 3, we haven't done that yet. So what I'm going to do is get rid of today's lab, because I want the Tuesday class to be able to catch up somewhat. So on Tuesday, the Tuesday lab will do the laser safety and the third lab. Okay. Third lab is not that, doesn't take very long. Actually, both labs don't take very long, so you can knock both of them off in one lab period. That way, everybody will be caught up next week. All right, good. So there's no lab today, unless you really want to hang out here. Yes, I am. I didn't forget. Okay, before you leave, hold on.
The quiz.